Section. Introduction. Let's dive into the world of neural networks. Not too long ago, transformers took the spotlight from recurrent neural networks, RNNs, as the preferred structure for natural language processing, NLP. Unlike RNNs, which keep track of previous inputs, transformers can directly access each token in a sequence. Recently, decoders, a type of transformer, have become quite popular. They usually generate their output in an auto-regressive manner, meaning the creation of each token depends on the computation of previous tokens. Interestingly, this auto-regressive nature aligns with the core principle of RNNs, which is to maintain a state from one step to the next. With this in mind, we redefine decoder-only transformers as a type of multi-state RNNs, MSRNNs, which are essentially a more generalized version of traditional RNNs. As the number of previous tokens increases with each decoding step, transformers can be seen as MSRNNs with an infinite number of states. We then show that transformers can be compressed into finite MSRNNs by limiting the number of tokens processed at each step. We also discuss previous work that applied compression policies to limit this capacity in pre-trained transformer-based language models. Our definition frames these works as converting pre-trained transformers from infinite into finite MSRNNs. Next, we introduce TOVA, a simpler yet more powerful MSRNN compression policy. TOVA selects which tokens to keep in the multi-state based on their attention scores. We tested TOVA on 4 long-range tasks and found that it outperforms all existing policies, and leads to minimal performance degradation compared to the infinite MSRNN, using, in some cases, as little as 14 to 18% of the context. We also analyzed the tokens kept in memory by our method. We found that not all recent tokens are important to keep in memory, and some can be safely dropped. We also discovered the importance of keeping the very first token in the sequence, and other important tokens such as possessive nouns. Our results shed light on the behavior of transformer decoder language models. While they are trained as infinite MSRNNs, they often perform in practice as finite MSRNNs. Our method also has practical benefits. It significantly reduces memory consumption during inference, leading to up to an 88% reduction in language model cache size. Now, let's briefly introduce RNNs and transformers. We'll assume a model with a hidden dimension size of d. RNNs are a type of deep learning architecture that processes sequential data in a recurrent manner. Each layer, often called a cell, is modeled as a function that receives 2 inputs at a time, a representation of the token and the hidden state from the previous time step. It then outputs 2 values, an updated token representation, and a new hidden state. The new hidden state is used for the recurrent computation over the next token, while the updated token representation is used as input for the next layer. Transformers, on the other hand, process sequential data in a non-recurrent manner. A transformer layer takes as input a sequence of token representations and returns a transformed representation. Each transformer layer consists of 2 main components, self-attention and feed-forward. The former operates over the entire sequence, while the latter on each token individually. Self-attention projects the input into 3 matrices and computes the interactions between tokens within a sequence. Section Summary. In this section, the authors introduce transformers as a replacement for recurrent neural networks, RNNs, in natural language processing, NLP. They demonstrate that the auto-regressive nature of transformers aligns with the core principle of RNNs, and propose redefining decoder-only transformers as a form of multi-state RNNs, MSRNNs. They also propose a compression policy called TOVA, which selects tokens to keep in memory based on their attention scores, leading to improved performance and reduced memory consumption. Section. Transformer decoders. In this work, we're focusing on decoders, which are a crucial part of the transformer model. These decoders use a technique called masking to predict the next token in a sequence. When we use auto-regressive decoding, we often store the K and V matrices to avoid having to recompute previous tokens. We're also introducing a new type of recurrent neural network, RNN, called a multi-state RNN, MSRNN. This is an RNN that uses a matrix of states instead of a single vector. The size of this matrix is determined by a function, which can either be constant or dependent on the input. Each row in this matrix can be thought of as a single state, making the entire matrix a multi-state matrix. If we set the function to always return 1, the MSRNN becomes a standard RNN. Interestingly, we can view transformers as a special case of MSRNNs with an infinite number of states. This is because, in a transformer, the number of single states equals the number of input tokens at a given time step. In this setup, the matrix of states in the MSRNN is equivalent to the K and V matrices in the transformer. However, in practice, transformer models are trained up to a specific length and often struggle to extrapolate beyond that. But theoretically, they have the capacity to handle infinite length inputs, making them equivalent to an infinite size MSRNN. This leads us to an interesting question. Do pre-trained transformers actually use this infinite capacity? To answer this, we define a finite MSRNN by setting the function to return the minimum of the time step and a constant. When the time step exceeds this constant, we apply a compression policy to fit the context into the memory restriction. This policy can be predefined or learned during training, similar to some RNN variants. We've observed that several compression policies have been proposed, which could be used to convert an infinite MSRNN into a finite one. One such policy implements a first-in first-out (FIFO) strategy, where the oldest state is discarded when the multi-state reaches its capacity limit. Another policy extends the FIFO strategy by also retaining the first few tokens. Previous work has shown that this policy significantly outperforms the FIFO strategy using as few as 4 early tokens. Another policy, similar to the previous one, keeps a fixed window of the recent tokens, as well as additional earlier tokens. However, it selects the non-window tokens dynamically by aggregating the attention scores throughout the sequence and keeping the tokens with the highest aggregated scores. The number of non-window tokens is typically set as half of the multi-state size. Preliminary results indicate that both variants perform similarly, so we follow and use the headwise version. Section Summary. In this section, the authors focus on transformer decoders and their ability to perform next token prediction. They also introduce the concept of multi-state RNNs, MSRNNs, and demonstrate that transformers can be viewed as a special case of MSRNNs with an infinite number of states. They propose a novel finite MSRNN policy called TOVA, which implements a first-in first-out (FIFO) strategy for retaining the most recent states while discarding older ones. This policy dynamically selects non-window tokens based on aggregated attention scores, resulting in improved performance compared to previous compression policies. Section. Our proposed policy, TOVA. We're introducing a new policy called token omission via attention, TOVA. Unlike previous policies, TOVA doesn't focus on the most recent tokens or those that appear early in the sequence. Instead, it keeps the top states based on the attention weights of the last token only. At each decoding step, we look at the attention scores from the current query to all the tokens currently in the multi-state, including the current token. The token with the lowest score is then removed. TOVA does have a slight bias towards recent tokens, as early tokens need high attention scores in all subsequent decoding steps to stay in the multi-state. However, our analysis shows that TOVA often drops a significant portion of recent tokens, suggesting that a fixed recent window might be too restrictive. Moreover, some initial tokens are kept for thousands of decoding steps, indicating their importance for successful decoding. We also found that TOVA performs better when operating layer-wise rather than headwise. In our tests, TOVA outperformed other policies, achieving results similar to those of an infinite MSRNN, a regular pre-trained transformer. Our experiments aimed to see if any compression policy could match the performance of the full, infinite MSRNN model. We tested different compression policies and used various benchmarks and transformer LLM families. We focused on long-range evaluations, including language modeling, long-range understanding, and generation of long texts. We used the PG-19 test set, a popular benchmark for evaluating long-range language models, and 2 test sets from the Zero Scrolls benchmark, focusing on long-range summarization and long-range question answering. For text generation, we asked the models to generate a long story. We sampled 100 unique stories from each model version, using different seeds. To compare the stories, we used GPT-4 as an evaluator. We only considered a win if the same approach was preferred in both cases. We used 3 state-of-the-art transformer decoder LLMs families, Llama 2, Mistral, and Yi. Each family offers a version with around 7 billion parameters, which we used for evaluation. For language modeling, we used the basic versions of the models. For the long-range understanding tasks, we also considered 3 fine-tuned versions. Lastly, for text generation, we used Mythologic, a Llama 2-13b version fine-tuned for story generation. For all models and tasks, we used a maximum input length of 4096 tokens. For the language modeling task, we split the texts into chunks of length 4096. For the language understanding tasks, we truncated the end of the example if it exceeded 4096 tokens. All experiments were done using bfloat 16 floating point precision over NVIDIA V100 GPS. Section Summary. The proposed policy, token omission via attention, TOVA, simplifies previous methods by retaining the top states based on the attention weights of the last token only. TOVA drops the token with the lowest attention score at each decoding step, making fewer assumptions and avoiding a fixed recent window or favoring early tokens. Experimental results show that TOVA dominates other policies and achieves similar results to the full, infinite MS-RNN model in terms of language modeling, long-range understanding, and text generation tasks. Section. Pre-trained transformers act as finite MS-RNNs. We're here to share our findings on how pre-trained transformers behave like finite multi-state recurrent neural networks, MS-RNNs. We've tested this theory across various tasks: language modeling, long-range understanding, and text generation. Let's start with language modeling. We used several strategies to evaluate our base models, including window, window plus 4, H2O, and our own TOVA policy. We compared these strategies against 2 benchmarks: a model with a smaller sequence length and no compression, acting like an infinite MS-RNN with a sequence length less than 4096, and a model with the full training sequence length of 4096, again without compression. We tested multi-state sizes that doubled in size from 64 to 4096. Our TOVA policy outperformed all others across all models and multi-state sizes, achieving results within 0.5 perplexity points of the top benchmark while using only a quarter or even an eighth of the full context length. Other strategies needed at least half of the full context length to achieve similar results. Next, we evaluated long-range understanding using instruction-tuned language models on S-quality and QASPER. We used a baseline where the model was given a shortened version of the example based on the MS-RNN capacity. For instance, if the multi-state size was 1024 tokens, the baseline used the example shortened to 1024 tokens. Again, we tested multi-state sizes that doubled in size from 256 to 4096. For long-range summarization, our TOVA policy consistently outperformed the baselines across all multi-state sizes and models. Using TOVA with a quarter or even an eighth of the full context yielded results within 1 point of the top benchmark. For long-range question answering, the gap between TOVA and the baselines was significant, sometimes exceeding 5 F1 points. However, TOVA needed half of the full context to perform within 1 F1 point of the top benchmark. In text generation, we found that limiting the multi-state size resulted in shorter generated text. For example, the average story length for the full model was 1,566 tokens, but this dropped to 1,361 with 256 tokens. Using a small multi-state size, 256 tokens, our policy lost to the top benchmark in 47% of cases, but this loss rate decreased to 19% with 512 tokens and further to only 6% with 1,024 tokens. Our findings suggest that transformer decoder language models, which are infinite MS-RNNs, often behave like finite MS-RNNs. In 2 out of 4 tasks, finite MS-RNNs using as little as an eighth to a quarter of the tokens yielded comparable results to the corresponding infinite MS-RNN, despite being trained with the full context. The other 2 tasks, text generation and retrieval question answering, seem to require longer context, though they still maintained comparable performance using half of the original context. We also found that not all tokens are equally important. Most of the tokens are dropped from memory as generation progresses. We observed that recent tokens are often preserved, but many older tokens are also kept. Only 73 to 76% of the tokens are recent, the rest being older. We also found that the very first token is crucial for the model, but other initial tokens are far less important. Some tokens, such as punctuation, special symbols, possessive nouns, and proper nouns, tend to be kept longer. Studying the role of these tokens is an exciting research direction for the future. Section Summary. The authors present their findings on the behavior of pre-trained transformer models in different tasks, including language modeling, long-range understanding, and text generation. They evaluate the models using various policies and multi-state sizes, and their TOVA policy consistently outperforms other policies in language modeling and long-range understanding tasks. The authors also analyze the token retention process and find that recent tokens are important, but older tokens are also retained, with certain tokens like punctuation and proper nouns being kept for longer durations. Section. Increased batch size using TOVA. We're going to talk about how we can increase the batch size using a method we call TOVA. As we've mentioned before, it's common to cache the K and V matrices when decoding transformers in an auto-regressive manner. This is a trade-off between decoding speed and memory usage during runtime. The amount of memory used is determined by two factors: the size of the model, like the number of layers and the hidden dimension, and the batch size. Since the model size is fixed, caching effectively puts a limit on the batch size during inference. However, when we decode transformers as finite multi-state recurrent neural networks, RNNs, the cached K and V matrices are compressed. This means that if we reduce the multi-state size to 1 over m, 1 per meter, of the original size, we can increase the batch size by a factor of m. This can greatly improve hardware utilization. As we'll show later, TOVA allows us to limit the multi-state to between 1/8, 1/8, and 1/4, 1/4 of the full language model's context length without a significant loss in performance. This means we can increase the batch size by up to 8 times. There have been several attempts to simplify transformers and bridge the gap between them and recurrent neural networks, RNNs. Some have used a hybrid approach that attends to recent tokens and hidden states at the same time. Others have replaced the self-attention layer with a convolution layer that can be applied in a recurrent manner. Some have adjusted the self-attention layer to maintain an RNN-like behavior during inference. One particularly relevant work presented transformer models with bounded memory. They showed that several transformer variants can be interpreted within their framework. However, these models typically treat memory as a single state, not as multi-state, meaning there's no explicit mapping from tokens to states. Unlike our approach, these models require a dedicated training procedure and can't operate on existing transformer-based language models. Recent work has tried to revive RNNs in natural language processing, NLP. The most notable work is S4 and its successors, which use state spaces to form linear RNNs. Other works have introduced new RNN variants that train effectively while reducing inference cost. Window attention is a simple way to construct a transformer with limited cache requirement. As we mentioned before, the H2O policy can be used to limit the cache size of transformers. A very recent follow-up work showed that manually caching specific tokens like periods and commas can further boost H2O performance. We showed that TOVA does this without manually selecting tokens. Lastly, some works have shown that the window plus I policy allows models to extrapolate beyond their training sequence length. The application of TOVA for extending the context size of language models is an interesting topic for future research. Previous work has shown that many transformer attention heads can be pruned. Some have shown that the dynamic attention in transformers can be replaced with static weights without a major drop in performance. We show that transformer decoders can be reduced to finite RNNs.